join. Okay,
Yeah.
so he's returning. I don't know what's going on. All right. Okay, recording started. Stage is yours.
Okay. uh, can I proceed without gavel, or should we wait for him? Or he?
I
He
think
just
he's
rejoined.
back. Yeah.
Okay, okay. Um, so I think as many of you know, that today's topic is about Politex. Uh, so we previously learned API and its performance guarantee, but unfortunately, API's performance guarantee contains a bit pessimistic term, which shows that API is a bit robust to function approximation error. And in contrast, as we see later, Politex is more robust to function approximation error. And this is very, I think, important because this means that even with, I mean, actually we will see later that API with infinite amount of data cannot beat Politex. Even it uses infinite amount of data, it cannot reach the suboptimality of Politex, the suboptimality Politex can reach. So in this sense, Politex is a very good algorithm, but there are some price you need to pay. Okay. Anyway, here's the table of contents today. So we will start with a quick recap of LSPIG, what it is, and its suboptimality gap due to functional approximation error. So this is caused by functional approximation error, and we will recall it. And later we will see that if this suboptimality gap due to functional approximation error is real or not. And it turns out that unfortunately it is, yes. And we will also try to see if it is possible to avoid it with any algorithmic change. And we will see that relatively simple algorithmic change allows you to avoid it. And this algorithm is called Politex. And in the end, I will talk about some notes. And I assume that all of you have read these parts. So I will quickly go through these parts, and I will focus on this notes, which contains some new results and that are not in the lecture notes, and some additional explanation to notes in the lecture note. Okay, so here's the pseudo algorithm of LSPIG, and it is LSPIG stands for least squares politicization with G-optimal design. So it needs G-optimal design. So given the feature map, it needs to find the core set C and optimal design rho, and it initializes theta -1 to k. And the main part of LSPIG is this part. So LSPIG repeats these updates for k times, and in the end, it returns a greedy policy with respect to phi theta k minus 1, which is an estimate of q pi k minus 1. Okay. And in this loop, it starts with updating a policy to a greedy policy with respect to this phi theta k minus 1, which is an estimate of q pi k minus 1. And for each element of the core set, so this Z is an element of state action space pair. And for each state action pair in the core set, it generates rollouts following this policy pi k for 8 steps. And then compute return estimate r hat m z by just taking the average of return you observed by generating rollouts. And after computing return estimate for each element in this core set, it updates theta k in this way. And this is actually equal to argmin theta of z rho z phi z t theta minus r hat mz squared. So it's just a least squares estimate. And that's why it's called least squares policy edition with G-optimal design. And this is LSPIG, and it's quite simple. And here is the performance guarantee of LSPIG. And it for any MDP feature map pair and any epsilon prime greater than 0, LSPIG can produce a policy pi such that its suboptimality gap delta is upper bounded by this, where this epsilon tilde m phi is defined like this. So it's the worst case worst case approximation error for Q pi, where pi belongs to the pi phi. And pi phi, large pi phi, is the class of phi measurable policies. So do you have any question?
Yeah, I was going to say, is there by using this G-optimal construction, do you get an improvement in the suboptimality gap? I see you have this squared in red.
No, so, well, it's actually not clear. So we will see later that if you choose a design in a bit bad way, you can show that this is tight. But it's a bit unclear if we can avoid it by choosing G-optimal design. I mean, design as the G-optimal design, but I guess it won't change a lot because later we will see that this quadratic dependence on the time horizon is tight, and the proof uses state aggregation as a feature map. And this state aggregation can be understood as a kind of tabular representation, and even with this tabular representation, you need to pay 1/1 minus gamma squared. So, and I guess in this case, G-optimal design actually, yeah, cannot do much. Yeah, let's see later. But I guess this quadratic dependency is actually a tight, even with G-optimal design. Okay, please, Vlad.
Yeah, just one question. The supremum over the policies of all phi measurable policies, is this like smaller than the class of all possible policies? I guess it is.
Yeah,
like
yeah, because this phi measurable policy, the class of phi measurable policies are included in the class of all policies, so it should be smaller.
And why is that required? Because I thought before we just assumed this was true for all policies, and now we have this. I guess this was used in the lower bound from what I recall, but.
So actually, if you look at the proof of LSPIG's performance guarantee, you can see that the policies appearing in the proof is only phi measurable policies. And you actually do not need to consider all class of policies, but you just need to consider class of policies that can be generated by LSPIG. Saba, what?
Yeah, related question to this. So if we would replace this fine measurable policies with all, I don't know, memoryless policies, would we get a bigger and smaller epsilon tilde? Would that be good for us or bad?
So it should be bigger than this epsilon tilde. So I think it's worse because
It's a worse
upper bound.
bound.
Yeah, upper bound is larger.
It's just a tighter bound based on the observation that the algorithm never actually uses a policy which is not phi measurable. So it doesn't, like, these algorithms do not use the states in any significant way. They only use the features of the states.
Yeah.
The state action pairs, actually, right?
Yeah, so this is a bit tighter than the previous upper bound you saw. I didn't see it, but you saw it, I guess. Yeah. And LSPIG can find a policy whose suboptimality gap satisfies this with a total runtime of this. So it's a polynomial of feature dimension d, time horizon, or effective time horizon, and number of actions, and 1 over epsilon prime. And here, actually, this epsilon prime is something you can control if you use more data. So if you don't care about the runtime, then you can make this epsilon smaller and smaller, and eventually it can be negligible compared to this guy. So, and as I said, this part is due to a function approximation error, and even with infinite amount of data, LSPIG cannot do better, or like cannot reduce this. So, okay. And in previous lectures, I didn't see it, but you saw it, that square root d is inevitable. I mean, well, it depends on the, which function or feature map you use, but in general, this square root d is inevitable. But is this quadratic dependence on the time horizon also inevitable? And it turns out that as long as you use LSPIG, the answer is yes, and that is proven by or shown by this theorem. And this theorem says the following. So for every discount factor gamma, there's a feature at the MDP M5, and it's stationary, or it's called memoryless policy in this lecture series. So memoryless policy, and the distribution mu over the states, over the states such that LSPI with access to two Q functions produces a sequence of policies, pi 0, pi 1, so on, such that this is satisfied. Okay, please, Vlad.
Yeah, but this just says, so it doesn't say anything with, like, if you're okay with suffering the square root d as well, right? Like, it doesn't say that, like, this is 1 over gamma squared is necessary if you suffer a square root d term, right? It just seems to say that, like, this is necessary if you don't want the square root d. I don't know if there's, like, maybe if you are okay with suffering the square root d, then you don't need the squared term. Is that, like, a possibility? I guess we don't know. Does that make sense?
Sorry, I don't quite get the question.
Right. So in the previous thing, in the previous slide, you just said the square root d is unavoidable,
Yep.
as we saw.
Yep.
Now you're saying the 1 over 1 minus gamma squared is unavoidable. We don't know, it seems like, whether the square root d times 1 over 1 minus gamma squared is unavoidable together.
Yeah, you're right. Maybe it's avoidable.
I guess the reason I'm saying is because in this lower bound, right, if I'm not wrong, that's had like state aggregation, in which is like a special feature map. But then in the other lower bound for the square root d, we chose like an adversarial one, kind of using jail lemma. So I don't know, like maybe there's something that's doesn't work if you have to choose this other feature map that suffers a square root d part. I don't know.
Yeah, you're right. Maybe it's
interesting. Yeah, I just want to add something small here. So surely you can, well, let's call this the error amplification factor, right? Like we are talking about either the square root of d or a 1 over 1 minus gamma squared is going to be there. So since we have a proof for both of them, the amplification factor is at least as large as the maximum of these two. But we don't know, the maximum of the two can be smaller than the product of the two. So this difference between, like, is it really the product that should appear, or is it the maximum that should appear? We don't know. If you ask me, I would say it's probably the product, but we don't have a construction. So that's I think that's an awesome problem to work out the construction, merging maybe the two proofs or whatever, figuring it out. It's not that trivial. Tadashi's is going to explain a little bit about this proof, right? And so we will see. It's an awesome problem, I think.
Yeah, I agree. Yeah, let's talk about it later. Okay, and anyway, let me explain this result. So the important point is this point. So this LSP, in this proof, LSPI can access to the two Q functions, or in other words, it is allowed to use infinite amount of data. And even if LSPI is allowed to use infinite amount of data, you need to pay you need to pay this suboptimality gap. And on the right-hand side, you are picking up the best policy. So even if you pick up a best policy among the sequence of policies, that's worse than this left-hand side, and you need to pay this suboptimality gap. Yeah, that's a bit unfortunate result. Anyway, so that's the result of LSPI. And as Zaba said, I will talk about the idea of the proof. And in the proof, the feature map is chosen to be a state aggregation. And state aggregation, if you try to write it down in an equation or math expression, it's a bit complicated. I'm not quite sure whether there is a simpler notation, but yeah, I would say it's a bit complicated. So suppose that the state space and action space is finite, and S has a partition, deep partition, or subsets of state spaces, so that if you take this union of this guy, it is equal to S. So it's a partition of the state space. And state aggregation, so phi j, or jth element of phi SA is this guy. So it's a bit complicated, but let's try to decompose it. So the first term is indicator function, which takes 1 only when the state S is included in this partition. So CO is just a CO function. And this second term is, yeah, it's a bit complicated. So I actually prepared a Python code a little bit, and it'll be probably easier to get the idea of the state aggregation feature. Or maybe you know it, but yeah, let me explain. So this phi is a vector of indices from 1 to 6. So it's just J here. Okay, and this CO is equal to CO of J divided by A. And it looks like this. And what it is doing, is that it is, okay, so these blocks with 1 means that these indices are for partition 1 of the, S1. And these two, indices with these 2 are for state partition 2. And so if state given to phi is in partition 1, only these indices take 1, and other indices are 0. And if the state belongs to partition 2, then these states with 2 are 1, and other states, these are 0. Okay, and this, and I guess this RAM, etc., is a bit complicated part, and that is actually computing this guy. So it's a index of actions, actually. So 1 means the first action, 2 means second, 3 means third, etc. So this part says that if your action is 1, then this guy and this guy are 1, and others are 0. Oh, actually, I explained them there. Okay, anyway, and after computing it, this phi j SA is, or phi SA is computed by taking the element-wise multiplication of those 2 terms. So this is, sorry, so this is checking whether which indices corresponds to partition 2. And this is checking which indices correspond to action 1. And after taking the element-wise multiplication, you get this. And this means that the state given to a feature map belongs to the partition 2, and action is action 1. Okay, that's all. Does it make sense? Okay, great. Yeah, that's the state aggregation. And let me jump into the idea of the proof. So the proof idea is quite simple. In this proof, we use this environment. So this environment consists of like a, I'd say, a bit complicated chain of states. So it consists of, these components. So each circle represents a state. And there are upper states and lower states. And in at every state, you have 2 actions, either move or stay. And in the upper state, if you choose to stay, that's a wrong terminology, but if you choose to stay, you actually move to this lower state. And if you choose to move, you move to lower state in the left to this upper state. And at the lower state, the situation looks a bit similar. So if you choose to stay, you stay. And if you choose to move, you move to the left state. And in this environment, stay incurs some cost. But the cost of staying at upper state is a bit smaller than the cost of staying at the lower state. So that's actually the important point. And for state aggregation, we aggregate a pair of upper and lower state like this. So these gray boxes indicate the group of states or partial states. So, okay, please, Jamin.
Yeah, I was wondering how can the agent reach the upper state?
It cannot reach to the upper state.
Right.
So I would say these upper states are introduced so that the proof makes sense, or so that the function approximation error occurs. And I think after a bit more explanation, you get the point why we need these upper states. So these upper states are just for proving a lower bound.
Okay, so it's only for calculating the error.
Yeah, they're just for introducing errors, I would say.
So the theorem was allowed us to choose an initial state distribution. Is any of the upper states going to be included there in the initial state distribution, or not even that?
So if your data distribution is data distribution obtained by following some policies, I think initial states needs to include these upper states. But if you I mean, if you fit the Q function with like some arbitrary data distribution, then you do not, how can I say, you do not need to assume that the initial states visit upper states.
Okay, okay, but like we are going to do a least squares fit to the
Yeah.
true function, and in a least squares fit, a distribution over the states is chosen in some way.
Oh yes, so
and
that distribution should contain upper states.
Yeah, because if they don't, then the upper states simply don't matter, and the state aggregation
Yeah.
has no effect, right? So in
Yeah,
a way,
exactly.
that's like they are there to distract the least solution, and
Yeah.
they will distract the least square solution as long as enough weight is put on them in a way, right? Which may happen inadvertently. If someone's choosing a distribution, they're like, oh yeah, why not choose this distribution? Let's try, and then you may end up with a situation like this.
Yeah, exactly.
Like off policy problem too.
Yeah. I think I will explain it soon. Anyway, so these are the like a situation, feature map, and MDP. And because we are using state aggregation, what it means is that, okay, for example, Q, let me U and Q estimate of QUS needs to be equal to Q estimate of this guy. So both Q estimate for the state at the upper state and lower states needs to be the same because we are using a state aggregation. And the agent cannot distinguish this upper state and lower state. So if you, and for these squares, when state aggregation is used, what you actually does is you just assign a weight to QS, no, not S, sorry, QUS, Q, or maybe let's go back to the previous one. So the feature map you see is always something like this. So there's only single one and others are zero. And what you do is that if you use least squares to fit the weights with state aggregation, you just assign some weights to each element and you adjust it. And this adjustment is so that the value is the average of values for like it's a bit difficult to explain. Values for data having the same feature vector. For example,
yeah, like maybe with the example you can explain what you mean.
Yeah.
Like what will be the value there?
Yeah. So let's say that I don't know how to stop it. So I don't know why, but after for some time these markers disappear and it's very annoying.
Which software are you using?
I'm using PDF Expert, but I don't know how to stop it.
I look it up.
Okay.
Don't worry about it for now.
I can do like this. So Q, it's quite faint. Let me. Okay. So, okay. Q pi of, let me call U and L. U and S Okay, you have it, and okay, Q pi. You have these values for like this aggregated state, and you fit Q delta your estimate of QU S is argmin W, I would call it W, of some distribution over states U or L and Q pi S. Oh, there are two S's, sorry. Minus W squared. So your Q estimate, I mean, actually, it's also equal to Q tilde LS. So Q tilde US and Q tilde LS are the same, and it is obtained by fitting weights so that this squared error is minimized. And it actually becomes some, I guess.
Just the weighted average of the values that you're fitting to, right?
Yep. Yeah. So, oh, sorry.
Vlad is trying to ask a question.
Yeah.
Sorry.
Well,
so I'm just so A and L are states here, right?
Sorry, it's U.
U and L are states. Yeah.
Yeah.
So I'm usually the second argument to the Q function is an action. What is this comma S being passed to the Q functions?
Sorry. So S is state.
No, but like when you write the argmin, then there is a Q pi S prime comma S.
Yeah, and also the argmin, doesn't that return the parameter vector? I'm just confused why.
In case this is a real, because you have these indicator vectors.
Yeah.
But I don't understand the S prime comma S. That's an A. That's just looks like an S. It's an A.
Oh, sorry. I mean,
like all of this, like the second argument, they all look like S. Oh, you have Q pi U comma S at the beginning of the slide. That's all.
Okay, let me.
They're A.
Okay. Let me. Yeah, let me change it. Yeah, let me change it. Yeah, sorry. A.
Okay.
A.
Okay. Right, and that argmin, because the feature vector is just a one-hot vector with feature value 1, you multiply it by the W. It's just a scalar.
So W is a scalar.
Yeah, that makes sense.
Yeah, because it's fun.
Okay.
As you say. Yeah, that's
right. Yeah, sorry for the confusing notation. Okay, and this result in Q tilde SA equals to rho of S Q pi SA. So if your data distribution rho contains both upper and lower states, like an estimate of Q tilde is like wrong a little bit. So they are just a weighted average of Q pi SA at U and L. So they are kind of mixed. And as I said, cost of staying at the upper state is lower a little bit compared to the cost of staying at the lower state. And this means that because of this weighted average, you overestimate the cost, not the cost, but you overestimate the Q value of staying at the lower states a little bit more. So this gives an agent the incentive to stay wrongly. Because, I mean, in this environment, only staying costs you. So the optimal action is just going left all the time. But because of this overestimation, the agent misunderstood that, okay, by staying here, we get a little bit more reward, or we can reduce the cost a little bit. So that's the, how can I say, underlying idea of the proof. And yeah, and that, I think, answers the question of jamming. So upper states are just prepared to cause this overestimation. And well, if the agent is behaving in this environment, they never reach those upper states. Yeah, that's the proof. And with a bit of calculation, you can show that the policy alternates between initial policy and the second policy. Yeah.
So how does it work? So what's the initial policy?
So sorry, initial policy is actually,
It's a good one, right?
It's actually not a good one. I looked at the proof, and the initial policy is not so good. So initial policy is, I mean, it's a bit arbitrary, but it is staying at this state and moving at this state, staying at this state.
So it's parity.
Yeah.
And then it's going to alternate.
Yeah. And so this is the initial policy. And after policy update, it changes to
staying in the other one.
Yeah, staying at other states and move, stay here, move, and stay here.
Right.
Yeah. And LSPIG switches between these two policies forever. And as a result, it cannot get closer to the optimal policy anymore.
Kind of stuck.
Yeah. So regarding Vlad's question about whether the lower bound is square root d divided by 1 minus gamma squared or not, yeah, maybe instead of using state aggregation, maybe we can choose a feature map so that the value of upper states goes to lower states a little bit, maybe. Like, so currently we are using state aggregation, but maybe we can, well, how do you write it? How do you write it? Yeah. Yeah, but maybe we can think of a feature map that results in the overestimation of Q value at the lower states somehow. I don't know, I have no idea now, but yeah, that's an interesting question.
Maybe one should introduce a lot of actions or something, and then don't mess with the structure with the state, just mess with the actions or something. I don't know. Like one has to experiment a little bit.
Yeah.
It's a good challenge.
Yeah.
Too much improves. Yeah.
So is there any intuition for why there's a squared? I like
oh, squared.
why two of these 1/1 minus gamma terms? I mean, I don't know. I don't like immediately see from this example why there would be, why you'd suffer twice the effective horizon.
That's a good question, and I have no answer.
It's basically, so okay, maybe it's just a lucky example, but or somehow these policies are pretty bad, right? Relative to the approximation error, that can be bad if the cost difference between the upper and lower states are smaller or bigger, right? And somehow, okay, for the whole effective horizon, so the range of the values would be, I don't know, age. And here we're talking about an h² difference. So already the epsilon has to be pretty small for that difference to kick in, right? Like these could be the worst policies, but only if the epsilon is small enough. Somehow.
Yeah, and one complaint about this proof is that the Q function also scales with epsilon. So the staying of cost scales with basically epsilon divided by 1 minus gamma. So if epsilon is too small, the scale of Q function is too small. And yeah, in that case, I'm not completely sure whether it's appropriate or not. Like that, yeah. Like if the scale of the Q function changes and if it becomes smaller and smaller, then your error is also smaller. And
no, but like the theorem statement, if you go back a little bit, so that theorem statement, okay, so it's a little bit fishy.
yeah,
it just says that like there is one case. It doesn't say that for every small enough epsilon, there is a feature as MDP such that the approximation error is at most epsilon, and these bad things are happening. But it just says that, well, there is some kind of features. But I think that the actual statement could say that, right? Like this is the scaling that you're talking about, that you could choose an epsilon, and for that epsilon, you can find a pair of MDP feature maps such that the approximation error stays below that epsilon for that pair, and these bad things are happening. And here, I mean, if the scaling, like here, you could choose the MDP based on the epsilon. That's all fine. But here, one has to notice that the value functions, yes, like if the rewards are between 0 and 1, and they will be, or costs or whatnot, then the scale of V star is just 1/1 minus gamma. And then this guy, the other guy, is squared of that. So if we only had 1/1 minus gamma, then this would be no miracle. Like it's fairly simple, like everything is scaled the same way. But here one is scaled quadratically, the other is scaled at best linearly with the effective horizon. So this statement is actually saying something highly non-trivial. Like even if the MDP and the feature map are chosen based on the epsilon, it's not simple.
Yeah, I agree that the result is non-trivial, but actually reward is not bounded to 0 to 1. Actually, it's bounded to 0 to epsilon divided by 1 minus gamma. So depending on epsilon, the reward scaling is changing. So V star is.
So what this says is that this is only valid, this result, if epsilon is smaller than 1/h or smaller than 1 minus gamma, right? So it's for small epsilons,
yeah,
which is fine, because that's where you kind of expect this to be true. For large epsilons, this cannot be true, because the range of the value function is 0 to h. You can't have an h² difference between the values of policies if the whole range that you can have is only h, right? Like you can't have that. You can only have it if the multiplier of the h² is small enough, smaller than 1/h. But that's fine. So the statement should be like, for every epsilon smaller than 1/h, for every age, for every epsilon smaller than 1 over h, there exists an MDP feature map such that the rewards are between 0 and 1 or costs, blah, 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 such that these bad things are happening. And that's what is being proven here. So I think that it is fine. It's a non-trivial result, and this is what you kind of expect. If epsilon is too big, then this can't be true. Unless you allow the rewards to be large or something like that you were saying. That's one way of making this true for any MDP, but then, like, okay, if you allow the rewards to be large, then I don't know, like everything scales with the scale of the rewards. Then it's kind of hard to see the scaling itself, because the epsilon, the approximation error, is kind of like, is it being scaled with the scale of the rewards or not? I guess the Q functions are scaled.
Okay. Anyway, let's move on. I think
Okay,
we're running out of time.
Yeah.
Okay, that's about the overview of the proof. And we saw that 1 over 1 minus gamma squared is real, and whether we are interested in whether we can avoid it. And we can avoid it by using Politex. And the Politex is the following algorithm. I mean, maybe I should call it as a Politex G, but so similar to LSPIG, it requires G-optimal design given the feature map to compute the core design, core set and optimal design, and let initialize initial vector theta minus 1. And this is just a definition. So Q bar minus 1 and Q hat minus 1 is defined as large phi theta minus 1. And let me recall that this pi means the projection. So because of least squares, sometimes this phi theta minus 1 might output some value larger than 0 or smaller than, larger than h or smaller than 0. And this pi is just cutting off values to h and 0. Okay, and similar to LSPIG, it repeats some updates. But the difference now is that pi k is not the greedy policy with respect to Q hat anymore. Instead, pi k is a Boltzmann policy induced by Q bar k minus 1. And we will see in the next slide the actual expression. So, okay, and except that change, the algorithm is almost the same. Minor change is that it returns all policies instead of the last policy. Yeah, so yeah, subtle but important change is that now pi k is defined like this. So it's a Boltzmann policy where ek is exponential of eta Q bar k minus 1, which is equal to exponential of eta times sum of previous Q function estimates. Yeah, so it is determining the policy based on the like sum of previous Q functions. Okay, and in the next lecture, we will see why we will prove rigorously that Politex has a better performance guarantee. But let's try to get some sense of why Politex performs better. So here you have the difference between the optimal state-wide function and V pi k, pi bar k. And pi bar k is defined as pi of I equals 0 to k minus 1. So it's a mixture of all previous policies. But what this means in reality is that this is actually equals to this.
Oh, it's an I.
What? Isn't it?
No, it was that, but in the average, the summing index was supposed to be an I, but it disappeared now, so it doesn't matter.
Okay. Okay, maybe I used a different.
Everyone understood. It's just the average of the value functions.
Yeah. And what you need to do in actual implementation is that in the beginning of the episode, you pick up one episode from all previous policies, and you run the agent with it. And then on average, you get the right-hand side. Oh, yes, please, Brett.
Sorry, can you just remind me? So in each iteration of Politex, you select the policy. Do you select one of the policies according to the softmax and then use that policy for that whole rollout? Or are you using this mixture of experts of previous value functions to select actions like over the whole rollout throughout?
No.
I don't know if you can see it. Yeah.
So during the learning, it uses this PyK. It's not a mixture policy. It uses the current policy for like a low rollouts. But after the learning, it needs to follow the mixture policy. I mean, I will also talk about later that you can actually use the last policy, but yeah, currently in the lecture notes, you need to follow the mixture of policies in the end. But during the learning, you just need to follow the current policy.
And so can you just clarify what you mean by current policy? The current policy now is it a randomly sampled policy from all the past ones by that weighting?
No, that's this guy.
Okay, so current policy is this softmax weighted policy of all previous like value functions.
Yeah.
Okay, and then can you just repeat what happens at the end again? At the end.
So at the end, you need to. I mean, okay. So this v pi k is actually equals to. So to k minus 1 v pi I. And what it means is that for the evaluation or after the learning, you like prepare all previous policies and you randomly pick up one of them and you run the agent.
I see.
And if you repeat this experiment many times, you get this performance guarantee.
And it's uniformly randomly chosen, just one policy.
Exactly. Yes, please, Jamin.
Yeah, I have a question. So here the pi bar k is like you select one of the policy uniformly each time and then follow that policy for the rest of the episode. I think it would be equivalent to choose one of the policy each time step.
No.
Is that correct?
No. So that's exactly what Sava prepared in the homework, and you need to prove it.
So
you prove that
is not equivalent.
They don't correspond. So interestingly, in imperfect information game, that's completely different from RL. But in imperfect information game or extensive form game, you can do something like mixing the policy in a bit different way, and you can show that it has this value function. So it is a single like a policy. It's not so you can like compute one stationary policy, and this stationary policy actually has the value corresponding to this guy. But that holds only in imperfect information game. If you have a loop in the environment, it doesn't hold. Yeah, but yeah, maybe that's just an information. Okay, so this is the left-hand side, the meaning of the left-hand side, and right-hand side has these two terms. And the first term is called a regret. I mean, this part is called a regret, and some theory from online learning can allow us to upper bound it. So, and we will do it next time, next week. And the second term corresponds to error term. So this q pi j minus q hat q, maybe I am a bit messing up with the notation, but this is just an error at the jth iteration, policy aversion error. And you can control it somehow with G-optimal design. And we can show that, and this part is upper bounded by this guy with a bit of algebra. Sorry, here should be -1. Yeah, this here should, here too. Yeah. So this part is a regret term, and it is independent of errors. And errors only come from this part, and this part contains only this guy. And if you have validation or policy, error terms usually have something like epsilon gamma squared max j, q pi j minus q hat j. And now you already see that this is validation and policy. So you already see that, okay, Politex doesn't seem to have a quadratic dependence on the time horizon.
It is your quick question. There is this I minus gamma pi star. Is it an inverse missing there?
Yeah, sorry.
Okay,
there should be inverse.
Yeah.
The inverse.
Sure. So that's where the 1/1 minus gamma is coming from.
Yeah.
Yeah, okay. Makes sense.
Okay, that's all about the main topics, and we don't have time, so we very quickly go through notes. It is known that, okay, let j pi as this mu v pi, which means that expectation of mu and v pi s. And the stationary point of j with respect to some set of memoryless policies pi, it seems it's a bit, there's some typo, but yeah, anyway. So stationary point satisfies this first order optimality condition. And if phi are state aggregation features, it is known that any stationary policy pi satisfies this result. And please look at this guy. So it's so there is only a linear dependence on the 1/1 minus gamma, and that's yeah. So if you find this stationary point, then you can enjoy this smaller dependency on the time horizon. And Politex can be understood as finding this stationary point, but also you can think policy gradient algorithm can be a special case of this. So if it can find a stationary point, then it should enjoy this smaller suboptimality gap or smaller dependence on the time horizon.
Sorry, in that equation with the 4 epsilon, is that nu supposed to be mu? Multiplying v pi and v star?
Oh yeah. This mu should be mu.
That's not like an occupancy measure by accident.
Yeah, sorry, that should be mu.
Okay, and this mu is like the initial state distribution or some state distribution, and the logic is like you multiply by the value function and you would get back like the same value function or something like that. The stationary point j.
So yeah, if mu is the initial state distribution, the interpretation of this result is that the expected return is close to the optimal expected return in some sense. And if nu is the stationary state distribution, yeah, maybe you can say something like that.
Did you say that Politex is a special case of policy gradient, or the other way around?
So both Politex and policy gradient are special cases of policy search algorithm.
Okay. Oh no, I was just going to ask. So you said if it can find the stationary point, where this gradient of j pi prime minus, like if you can find it quickly, it gets a small regret.
Yeah. So, yeah.
No, the reason I'm asking is, so if it can't find it, like let's say I was just thinking of Jincheng's result, and maybe you have some bad initialization, and you placed too much weight on a suboptimal action.
Mm-hmm.
And maybe you need a lot of steps in your softmax step to kind of place weight again on the optimal action.
Yeah, right. So policy gradient might not be, or might require so many data.
Mm-hmm.
But Politex won't. The difference is because I would say, maybe Taba disagrees with this, but I would say Politex is a natural policy gradient. At least they correspond in a linear function approximation case and on policy case. And in case of natural policy gradient, actually, if you look at their, okay, so natural policy gradient updates the policy in the same way as Politex. But the natural policy gradient is on policy algorithm, but this difference actually disappears if you evaluate a policy with least squares with, for example, experience play. And in this sense, Politex is a kind of natural policy gradient with off-policy data.
So this off-policy data help? I guess maybe what I want to know is,
yeah, it seems it helps.
Does this constant that you see in the policy gradient setting also come up here, or is there something we're doing to is it something to do with the initialization? Is it the way we collect data? I guess maybe that's what I was trying to understand.
So both in Politex and natural policy gradient, I think the phenomenon that Jincheng found won't occur because of the use of natural gradient. So if you go to, in case of policy gradient, if you go to the edge of simplex, then the updates becomes very, very slow, right?
Yeah.
But in case of natural policy gradient, it won't occur. If you go to the edge of simplex, then thanks to the inverse of Fisher information matrix, the step size becomes effectively bigger, and step size almost the same in simplex everywhere.
Oh, okay. So in this version of Polytech, we do have full gradient information.
Yep.
Okay.
Okay, so that's a result. And I guess I don't have time to explain this lastly data convergence of Politex, but it is possible with a bit of effort that the Politex actually shows the lastly data convergence. So previously we had B pi bar K. So previously we had P pi bar K. But here we don't have bar. So we are using the last policy. And still, we can show that Politex shows the last data convergence. Yeah, I will skip it, but somehow we can do it. And maybe I should explain this very quickly. But in case of state aggregation, previously in LSPI's performance upper bound, we had this square root d. But in the lower bound, we saw in this lecture didn't have this square root d. And the question is, what's the source of this square root d? Or why we don't have this square root d in state aggregation? And this square root d comes from upper bounding extrapolation error in proof. So previously we upper bounded. So this is extrapolation error of how can I say, fitting this phi z t theta. And we upper bounded this guy with this and this. And basically, this is error caused by sample estimates or, I don't know, some function approximation error. And we upper bounded the rest of this term by square root d. And the reason why we have square root d here comes from upper bounding this guy with square root d. But in case of state aggregation, it can be upper bounded by 1. And it's a bit with a better choice of design. So instead, maybe this corresponds to G-optimal design, but I'm not sure. But we can choose the design in the following way. So we pick up one element, Si, from each partition and let design like this. And then the core set becomes something like this. And we can show that G rho is 1 divided by AD times identity matrix, and phi SA T transpose times phi S prime A prime becomes 1 if and only if those S and S prime belongs to the same partition and actions are the same. And a bit of calculation allows you to show that this term, which is previously upper bounded by square root d, is equal to 1. So we don't have square root d dependence anymore. Okay, and in addition to LSPIG, we can think of LSVIG, in which false citation is replaced with validation. And you can actually show something, a performance guarantee similar to that of LSPIG like this. But the definition of function approximation error is now a bit different. So it's error with respect to one-step Bellman update. Okay, that's related to assignment. Well, you need to show it in the assignment. Okay, and finally, so here the definition of error is different from the definition of approximation error in LSPI. So this epsilon BOO and epsilon we had before are not comparable. But in case of linear MDPs, they become comparable. So an MDP feature map pair and phi is said to be approximately linear if there are two positive scalars such that the error of fitting reward function is zeta r, and error of fitting, basically fitting state transient dynamics is zeta p. And if these bounds hold, or if these equality holds, we can show that for any pi and function over state action pairs, infimum of this guy is upper bounded by this. So this is the worst case. No, sorry, this is the error of fitting r plus gamma p and pi f with phi theta. And if you choose f to be, for example, v pi, then this part just becomes q pi, right? So you can say that if, I mean, in case of policy policy iteration, this like epsilon we had previously is bounded by this. And also you can choose f to be this guy, phi theta, no, pi phi theta, and you can show something similar. And in the end, you can show that in both cases, epsilon and epsilon BOO are bounded by zeta R plus gamma zeta P. Oh, no, sorry. Aha. Plus 1 over minus gamma, gamma zeta P. Yeah, because F is bounded by H. Oh, I have it there. Okay, and that's all today. And if you have any question, please free to ask.
Yeah, I have another question.
Yeah, please.
That note about being able to use the last policy, is that in a paper? Like, where's that result? And is that only work for this G-optimal design stuff? I guess the reason I'm asking is that paper that Chaba shared earlier, the confident Monte Carlo LSPI stuff, has a Politex variant in it, and where they construct the core set. I think it was recently updated with it. And there they still choose the uniform policy at the end. I was just wondering whether you can use the same idea there. Are we just like, yeah.
Okay, I think you can use the same idea. And actually, this result is contained in a paper we wrote with Chaba and submitted to code. And we are preparing archive version. But yeah, maybe we can share a draft version now. Now or later in the chat.
That's
okay. It's just good to know because I remember being interested in this last year. So
maybe
yeah,
maybe we can go through the steps of this in the next lecture if time permits.
Yeah, sure. Yeah, and it seems that this is also not known also in natural policy gradient literatures. They seem to still use the uniform policy, uniform or mixture policy. So this is, yeah, an interesting result, I think. Because nobody uses mixture policy. You just use bus policy, right?
Yeah, I was looking at people when you were saying this mixture policy of like, how many stunned faces do I see that you're recommending to use this mixture policy, which could be horribly bad if you happen to choose a policy that was produced early on. It's just an arbitrary policy. And you're gonna follow it. It's like, okay, maybe on expectation it's not so bad, but like who has time for waiting for these expectations to, like get close to their average? Like how many times do you want to use this policy? If you only use it once, like who cares about that unexpectation it's gonna give it, right? Like the variance can be terrible.
Yeah,
it can kill the
I
same.
agree.
It's just like, yeah.
Don't you to some extent have to use these mixture policies just to hedge against, like, maybe you've been following this policy for a while, but it's actually not optimal considering it's optimal considering the data you've observed, but not optimal considering the MDP. Maybe
it's just a bad choice. I think it's just like a shortcut. Like I never thought that anyone in their sane mind would ever try this. If you see that like someone saying that a mixture policy is good enough, then you know that at least one of the policies has to be good enough. So then what you can do if you have a simulator and you trust it is that you just measure which policy is the best policy based on the simulator. It doesn't cost you much, and just run with that policy. So that will not increase by much the sample complexity. So that's why I never, like when we wrote these Politex papers, I was never concerned about this average policy. I never thought that anyone in their sane mind would use this mixture policy. But I saw that like if people wanted to use this algorithm, they would look at all the policies that are produced, just run quick simulations and just choose the best policy based on quick simulations. and then go with that one. So that was my taking it. Like maybe it was never written down. My bad, but
Okay, I thought it was
yeah,
like an artifact.
the mixture is a horrible choice.
I mean, don't you kind of do mixture policies when you even run exp3 in a bandit setting? Like you
Yeah,
technically.
but like it's kind of like I guess like in the community, everyone knows that if you have a stationary environment, then you have the luxury to actually select a policy, then you can do much better than just like running with an average, right?
Okay, because I guess the question would just be when do you like stop? Like when do you assume that you have enough information about your stationary environment in a sense? Okay, I guess that would be the hardness.
Here you have an MDP, it's completely stationary EXP, it comes from the bandit literature where you have adversaries, and that it's different because you're worried about the regret as you go. And there it's okay. And then when people prove these results, maybe you're thinking about the game theoretical results that you're playing to of these adversarial EXP strategies against each other or exponential weights against each other, and the average of the action choice distributions converges to Nash equilibria. So in the zero-sum setting, yeah, I guess there you can really compute the average because you are in a way in a tabular setting, so you can just like compute the average. And so there was this question, Jim, and I don't know, you were suggesting that maybe you should, like in every time step, you should choose uniformly at random one of the policies. So there, because there are no states, they are really the same. So then it's fine. Then it's a bona fide strategy. But here it's really questionable. But you will see that it's not so simple to just like, you might think that, okay, adding this extra randomization in every step is going to produce a better policy necessary, but like, is that really true? So you will see that in the assignment. But this result that Tadashi is talking about, last iterate convergence, it kind of trumps it all. Because once you know this, then you don't need additional simulations
so you guys got it
to use. Yeah.
Okay, so you got around this artifact of having to use a mixture of policies.
Yeah.
Oh, sorry, I consider it an artifact of maybe
it
like
is
a previous.
It is an artifact. I'm like, yeah, it's like it's easy to write a proof for that. I mean, once you have that result, then you know that like with almost no additional effort, you could also select a good policy. It is not elegant. That's the only thing. It is just not nice. Like it is much nicer to say that, well, you can as well use the last one.
Okay, so I guess how'd you guys get around? High level, do you guys? I guess we'll all find out in the next lecture. High level, how you got
Next
around
lecture.
this.
Yeah, exactly. So now that we have talked about so much upon this, we really have to go into it.
Okay. Oh, and this is the submission I keep hearing about.
Yeah.
Yeah.
All right. I think we should finish for today. Thank you, Tadashi.
Yeah, thanks.
Okay, so the next lecture might be in person. We're gonna discuss it in Slack. It is likely in person. If it's in person, maybe we're gonna try to stream it or whatnot so that other people can also join. Whoever not present, we can probably just like use a Mac and like kind of capture the vibe, what's in the classroom.
Does anyone actually have a tripod for a phone, like a phone tripod?
I did some testing today. I'll share with you guys after.
Okay. We'll figure out some technical solution. All right. Okay. See you.
See you.